Today we will be working with cones. To begin, we need our definitions. First, let's look at the cone depicted, cone AoB here. You'll see that this is a right circular cone. It's a right cone because line AO is perpendicular to the plane of the base, which is circle O. And it's a circular cone because the base is a circle. There are cones which are not circular, and there are cones which are not right. But for the most part, we will not be working with either of those types of cones. Our cones will be right circular cones. We'll call them a cone for short, or a regular cone. The vertex of a cone, just like a pyramid, is the point where all of the faces meet, and the axis of the cone, just like a cylinder, is the line that reaches from the vertex to the center of the base, and that is the axis. The slant height of a cone is the height of the lateral surface. And so on cone AOB here, our slant height is AB. The volume of a cone is similar, if not exactly the same, to the volume of a pyramid. If you recall, to find the volume of a pyramid, we take 1/3 the base times the height. Since on our cones the base is a circle, the area of the base is pi r squared, and the height will still be h. So our volume formula is 1/3 pi r squared times height. And that is all we need for our definitions. From there, we will work more facts out about cones over the next 5 problems. Starting with 15.4, what is the shape of the cross-section of a cone that contains the axis of the cone? So the axis of the cone is AO, and if we had a plane that contained that line, what would the shape be depicted? Another way to think of this is if I put my cone through a clear pool of water along the axis, what shape would be just resting on the surface of the water? We'd have the vertex, and we'd have the diameter, and this would be a triangle. What is the shape of a cross-section of a cone that is perpendicular to the axis of the cone? So if we had a plane that's perpendicular to the axis of the cone, if we cut the cone perpendicularly, what shape did we leave behind on the top of the cone? A circle, because a plane slicing through a cone will cut out a circle. In 15.5, we are going to try to find the formula for the lateral surface area of a right circular cone with base radius r and slant height L. The first thing we'll try to do is look at the result of 14.9 and try to take a guess at the formula from there. And that's going to be kind of fun. Let's look back at 14.9. In that problem, our solution for the lateral surface area of a pyramid was the side length for the base of the figure at the bottom times the slant height over 2. Since these were all triangular faces, we needed to use the area of a triangle. And then we multiplied that area of a triangle times however many faces we had. In this case, though, we don't have any faces. Cones have one lateral face, and it stretches all the way around. And they have one base edge, which also stretches all the way around. So maybe that's it. Maybe that can be our guess. We'll multiply the circumference of the base times the slant height. What's the formula for circumference again? That's right, it's 2 pi r. Times the slant height. Okay, well that's a good guess. Let's see what the real answer is by going onwards. So in B they ask us, let's see if we can unfold this shape. You know, three-dimensional geometry is always about not the magic of 3 dimensions, but taking 3-dimensional things, thinking of them as 2-dimensional. And that makes everything so much easier. That's how computer graphics work. This is how, for the most part, machines, welding machines, CNC machines, wood cutting machines work. They rely entirely upon taking the 3-dimensional object or space we want to manipulate and turning each of those problems into 2-dimensional problems that can be solved. So if we unfold a cone by cutting along AB, what shape do we get? We get something like this. And let's label our L and our R on this. Well, we don't have an R on this. This is just the lateral unfolding of our pyramid, or of our cone. So since this is just the lateral unfolding of our cone, there's no R here. There's only the L, which is here. But do we know what this length is here? It's the circumference of this circle. So we know it's pi r squared. Sorry, 2 pi r. And since we're dealing now with a portion of a circle, with an arc segment, we can find the relationship between the area of this arc segment and the length. We can find the ratio of the radius of our base circle to the radius of our circle sector that we have depicted in white. So the ratio of these two circumferences, the circumference of, let's call it circle O, to the circumference of circle A, is 2 pi r over 2 pi l. And these cancel out. And so it's r to l. So the area of the sector depicted is the area of circle A times r over l. So what's the area of circle A? Area of circle A is 2l squared, is pi l squared and then I use my ratio of the circumferences, r over l, figure out what this sector is. That's our lateral surface area for a cone. That's a pretty complicated proof, I think, but following along should help you realize the type of thinking that geometry can give us. We can take something that's not obvious and make it obvious. Alright, now we're going to deal with a simple application problem. Find the volume of a right circular cone that has a radius of 6 and a slant height of 8. Our radius is 6 and our slant height is 8. It's very important to always notice the distinction between the slant height and the altitude or the axis. So here we're clearly dealing with a right triangle. What was our formula for volume again? It's always helpful to rewrite your formulas when you're doing a problem so that you don't mess up with silly algebraic mistakes. Pi r squared times height over 3. Okay. So we know what our r is, but we still need our height. How are we going to find this? Well, we have a right triangle, and so we know that our height equals 8 squared minus 6 squared. 6 times 6 is 36. It's not 32. It's square root of 28, which is 4 times 7. Leaving me with 2 and 7 for my height. Alright, now I can just plug everything into my volume formula now that I have h and I already have r. And that will give me pi 72 root 7. But I forgot something. As usual, I forgot to divide by 3. So pi equals 24 root 7. So the volume equals pi times 24 times root 7. That was 15.6. Not too bad. It's always nice to do these application problems because they give us a good confidence booster. Even for me, I need those confidence boosters in the course of geometry. Let's look at 15.7. A semicircle is rolled up to form a cone as shown. You notice that this is a similar rolling up as we had previously, but this time it's a semicircle. This is going to give us a very particular type of right cylindrical cone, right circular cone. The radius of the semicircle is 8. What's the volume of the cone? Now this one's very important to label correctly. What is length AB? That is 8. What is length AB prime? It is also 8. What is length AC? That is 8 as well. So that's all of our slant heights. And that's all we have to allow us to find the volume of this cone. What's the other element we need to find the volume of a cone? We need the radius. So if we know that this is 8, and this is 8, do we know what CB is? Here's a clue. Let's look back at our first figure here. before this cone is folded up, notice that B and B prime are actually the same point. They're folded over on top of each other when the cone is formed. That means from B to B prime around the circle is the same as the circumference of our circle. So what is the length of B to B prime on this semicircle? So the semicircumference of this semicircle, the semicircumference of this circle A is 2 pi r over 2, which gives me 8 pi. So that's the circumference of this circle here. It's also 8 pi. Circumference equals 8 pi. Now if the circumference equals 8 pi, then we should be able to find the radius, because that equals 2 pi r. My 2 cancels out. I divide by 2, reducing my 8 to a 4. I divide by pi, getting rid of both my pi's. And I get 4 equals r. And now I have everything I need, I believe. We have our slant height, we have our radius, but we don't have our real height. Since our problem is to find the volume, we need this axis. Luckily though, we're looking at a right triangle. Clear as day to see. So AO equals 64, that's 8 squared minus 4 squared, 16. Square root of 48. And now we have everything we need to use our volume formula. We have our height, we have our radius, and now for volume, pi r squared. Don't forget to divide by 3. 16 times 4 is 64, root 3 over 3. Does 3 go into 64? 1, it does not. So, that's it. We have our answer. Volume equals pi times 64 times root 3 all over 3. And that is 15.7. Our last problem for today is 15.8. And this one's pretty quick actually. The cone is cut in two pieces by a plane perpendicular to AB at point X, where AX equals 6. Find the volume of the two smaller pieces thus formed. Alright, so let's get some drawing time in and label this properly. AB equals 9 and BC equals 12. And for this problem, I think it makes sense to then draw our two separate figures that we're making. So we have our plane that has cut our cone into two pieces. So we see that our top piece is still the cone volume of our smaller cone, and our bottom piece is kind of dog bowl. In any case, we have two similar triangles, like a beheaded cone, AXY, if you will, and ABC. And if we know what AX is, and we do, AX is 6, we can figure out the ratio for these similar triangles. We can figure out what XY is. So 6/9 equals XY/12. You can do the cross multiplying trick, 6 times 12 and 9 times XY. You'll wind up with 72 equals 9XY. Divide both sides by 9 and get 8 equals XY. Having that, we can find the volume of AXY, pi 8 squared times 6. That is 384 pi. But we forgot something. What did we forget? To divide by 3. Always remember the volume, so that will equal 128 pi. Alright, so how are we going to find the area? So how are we going to find the volume of this remaining figure? This might seem like a hard thing, but in fact, think a little bit more backwards. If we find the volume of the whole cone and subtract the volume of this smaller cone, which we just found, we'll be left with the remaining section. So that's all we'll need to do. The volume of this cone is pi 12 squared times 9. Divided by 3. Never forget to divide by 3. Make sure you do the exponents first, otherwise you're going to get yourself very messed up. Lastly, we'll merely subtract. Minus 128 pi. And that will give us 304 pi. Great. And that is it. 4 cones. Until next time, my perseverant friends. Arrivederci.